Good morning, calculus class. Okay, so today we're going to talk about the last two tests, and we'll start with the ratio test, and I'm not going to talk you through it until I get to a problem because it relates to things we've already talked about. So the idea is, you guys remember the rules for a geometric series convergence. If the r was between -1 and 1, or the absolute value of r was less than 1, then the series converged. Well, remember, r stood for ratio. So the idea behind the ratio test is that if we can look at the relationship between one term and the next, eventually, as n goes to infinity, it's going to behave similarly. So if the ratio of one term to the next, if the next term, for example, is about half the size of the previous term, then we know eventually it's got to go to 0, and it goes to 0 fast enough that it's going to behave similarly to a geometric series. So how does this work? Well, if the ratio between one term and the next, so if the next term is bigger, so greater a ratio of 1, greater than a ratio of 1, then it's going to diverge. If it's smaller, it's less than a ratio of 1, it's going to converge, absolutely. And if the ratio tests, like the ratio from one term to the next, is exactly 1, it's inconclusive and you can't draw a conclusion. So let's look at what this actually looks like for a problem. So on number 1a, it says, apply the ratio test to the following two series and show that the inconclusive results can happen for both convergent and divergent series. So let's look at how this works. So the sum from n equals 1 to infinity of 1 over n. So we really need to look at the n plus 1 term compared to the n term and divide them. So I will take 1 over n plus 1 and divide it by 1 over n. And that's the limit of this as n goes to infinity. So eventually, along the way, somewhere down the line, how do these two terms relate to each other? Now, if you divide by a fraction, this is really multiplying by the reciprocal. And of course, 1 over n plus 1 times n is the limit as n goes to infinity of n over n plus 1. What do we know about that? As n goes to infinity, it's equal to 1. So what does that mean? It means the ratio test is inconclusive. Now, we should already know what this series does, because we've talked about 1 over n before. This diverges, so you can see that if we get an inconclusive result, it can diverge. But what about the same thing, but 1 over n squared? Okay, so same strategy. We need to look at the n plus 1 term and the n term. So 1 over n plus 1 squared over 1 over n squared, and we're taking the limit as n goes to infinity of this thing, which is the limit as n goes to infinity of 1 over n plus 1 squared times n squared over 1, which is the limit as n goes to infinity of n squared over n plus 1 squared, which is still 1. So you can see the ratio test is still inconclusive, but we know 1 over n squared by p series actually converges. So you can't actually draw any conclusions if your limit is 1. If it's anything else, if it's a number bigger than 1, if it's infinite, or if it's a number less than 1, you can draw a conclusion in this test. But for these, you can't. So what does it look like when we get a problem where this actually works? Let's look at 2a on page 2. It says determine the convergence or divergence using the ratio test of this monster 2 to the n over n factorial. These are going to be a little trickier. You really have to understand how factorials work. What's the n plus 1 term? It would be 2 to the n plus 1 over n plus 1 factorial. And I have to divide these two things and take the limit. So the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. Now again, if we flip the denominator and multiply instead, it's 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. What I'm going to do now is group my terms according to what they're like. Limit as n goes to infinity of, so I'm going to switch these two denominators so we can see what's happening. 2 to the n plus 1 over 2 to the n times n factorial over n plus 1 factorial. Okay, so let's see what we can do here. Most people will be able to see on the left, this has exactly one more 2 than the denominator has in the numerator, so this is just going to be 2. But what do we do with n factorial over n plus 1 factorial? It's about what it means to be a factorial. So let's talk about, say, 9 factorial divided by 10 factorial. There's an n and an n plus 1. 9 factorial is 9 times 8 times 7 times 6 all the way down to 1. 10 factorial is 10 times 9 times 8, again, all the way down to 1. So both the numerator and the denominator have all the exact same numbers except for that last one, the 10. It has one extra number. So similarly, n factorial can stay, but n plus 1 is just n plus 1 times the rest of the numbers down to 1, which would be like n factorial, which allows us to take our n factorials and cancel them, leaving a 1 over n plus 1. Now when I multiply these two things, it's the limit as n goes to infinity of 2 over n plus 1. Now what happens as n goes to infinity? It becomes 2 over something infinitely large, which is 0. So what does that mean? That means the ratio of these terms eventually gets smaller and smaller and approaches 0. Why? Let's look at this first term. What happens to 2 to the n as you go up once every term? You multiply by 2. What does n factorial do? Well, the difference between 5 factorial and 6 factorial, you multiply by a 6 compared to what you have previously, and then a 7, and an 8. So eventually the denominator is multiplying by bigger and bigger and bigger numbers, so it's going to be overpowering that 2, which means the 2 to the n is rendered irrelevant. I mean, it's not irrelevant, but by comparison, the size increased by 2 is nothing compared to the size increased by multiplying by a larger and larger n. So what do we conclude here? By the ratio test, this sum from n equals 0 to infinity of 2 to the n over n factorial is absolutely convergent. And we will do more in the next video, but that's a starter for the ratio test.